Power in AC circuit questions and answers.
Okay, so lovely people, we are back here and today we are solving some examples on the power in AC circuits. We want to solve some examples on power in AC circuits. So let's take the question together. Let's all read the question together.
A single-phase motor connected to a 400-volt 50 Hz supply is developing 10 kilowatt with efficiency of 84% and a power factor of 0.7 lagging. Calculate A, the input kVA, B, the active and reactive components of the current, and C, the reactive kVA.
So the parameters from the question, we are having a voltage which is 400 volts. We are having a frequency of 50 Hz. We are having a power of kilowatt, 10 kilowatts. And having the efficiency. So the efficiency was 84% efficient. And we have our power factor, which is 0.7 lagging. So these are the things we drew out from the question. Now the question is asking us to find A, the input kVA. The question is asking us A, that is to find the input kVA. But remind me that when we are talking about the power in the AC circuit, I did what we call the power triangle. So out of the power triangle, I talked about the active power, the reactive power here, the active power, which is the real power, and the apparent power, which is the total amount of power that is running through. And here we say you should calculate the kVA. And you know that the kVA is simple, the kilovolt ampere. And the kilovolt ampere means that we want to calculate the input apparent power. The input apparent power. But before we can do this, the 10 kilowatts we're giving here is the power out. The power that was flowing out of the system. So if you want to find the power that is in, it is the power out all divided by the efficiency of the machine. So the amount of power that left the machine due to its efficiency was the 10 kilowatts. So if you want to find the amount of power in, it is the power out divided by its efficiency. So we get 10 divided by 0.84, which gives us 11.905 kilowatt. Okay. So since we have this power now, then we can now find our S. Okay. So now finding the X is very simple. That is the input kVA. It is the power in divided by the packing factor, or the power factor. So the power in divided by the power factor, we've already generated the formulas already. So now with the power in, we have 11.905 kilowatt divided by 0.7. And when you do this, you are getting 17.007 kVA. That is kilovolt ampere. Kilovolt ampere. Okay. Now the second question says we should find the active and reactive components of the current. The active and the reactive components of the current. So now the active and reactive components of the current. Okay, so now the active and the reactive components of the current, realize that here there is a current that will produce here that will take through the active part. So let's say that current that will take through the active part is IA. Here there is a current that will pass through the reactive part. Let's say that current that will pass through is IR. So now what do we see here? We can draw a diagram. Let me draw it here. So this is the reactive part, the active part, the apparent part, which is the S. So the S contains, in terms of current, the S will contain the resultant current. So the current that will pass through the active power is IA. The current that is through the reactive power is R. And this is our theta. And we said the cos of the angle phi is the same as our power factor. So if it's the same as the power factor, how do you find the active component of the current and the reactive component of the current? We can find the resultant current over here, which is I. So when you get the resultant current, then here can be I cos theta. So the resultant current cos theta, cos this theta, that is the power, will give us our IA. Okay. So now when you come here, S is equal to IV. So here, we know our voltage, we know our S. So we can find the I. So which implies that our I, that is our resultant current, from through the apparent power to resolve in the apparent power, is now equal to our S, our apparent power on V. So our S found was 17.007 times 10 raised to the power 3 because it is kilovolt ampere, all divided by our volt, which is 400 volts, given in the question. So now, when you do this, what you get is that the volt is cancelled the volt away. So when you do this, you are getting 42.518 ampere. 42.518 ampere. Okay, so now this becomes the total current. So the current through the apparent power, or the current that's producing the apparent power, is 42.578 ampere. Okay. So now we can find the active component of the current, which is IA. We can find the active component of the current, which is IA, and that is I cos phi. But cos phi is always the power factor. So therefore, IA is equal to the 42.578 times the power factor, which is 0.7 larger. So the IA will give us 29.766 ampere. So this is the value of the IA. Okay, so we've gotten the IA now. We want to find our IR. Our IR. Because we don't know the value for the theta, for the phi, or the angle, we can't just, because the IR will be what I sine the angle phi. Because we don't know the value for the time, we can't just use it. So we just have to use our magnitude approach, current approach here to get it. So now here, what we can say is that I will be equal to I, the square root of IR squared plus IA squared from this diagram. So we can find IR, which is equal to the square root of the I squared minus the IA squared. So therefore, our IR becomes our I, which was found here, 42.578 ampere, the square minus IA, which is 29.766 square. Okay, so when you do this, your IR will be 30.361 ampere. 30.361 ampere. Now the C aspect of the question says we should find the reactive power. The C aspect says we should find the reactive power. And the reactive power, we know, is measured in the unit of volt ampere reactive. Volt ampere reactive. So the reactive power, which is Q, is always VI sine theta. It's VI sine theta. So anytime you draw the curve, this is the Q, which is, so this, if here is the theta, this is VI sine theta, and the P is equal to VI cos theta, and our S, the apparent, is equal to IV. So this is how we find the Q. But take note that the I sine theta, so this aspect of it, the I sine theta, is IR in the question, and it's the current we found here. So therefore, you can say the Q is equal to V IR. And we have our V already, which is what? The voltage, which is equal to 400 times the IR current we found here, 30.361. And when you do this, you are getting 12.144 kilovolts ampere reactive. kilovolt ampere reactive. 1.44 volt ampere reactive. Okay. So that is the value for the question. So kilovolt ampere reactive, 12.144 kilovolt ampere reactive. Okay. So now, this brings us to the end of the first question. Let's quickly take the second question and we bring this session to an end.
An
Okay, so let's
EMF
all read
whose
the question
instantaneous
together.
value is given by 283 sine 314 T plus pi on 4 volt is applied to an inductive circuit, and the current in the circuit is 5.66 sine of 314 T minus pi on 6 ampere. Determine A, the frequency of the EMF, B, the R and L, and C, the power absorbed.
On the second question, these were the parameters you can draw out of this question. Now we had a voltage that was given as 283 sine of 314 plus pi on 4 volts. You have a voltage that was given as this, and you have a current IL through an inductor that was given as 5.66 sine 314 plus pi on 6 ampere. So this volts. Okay. So this is what we get from the question. Now the first question says that we should calculate the frequency of the EMF. The frequency of the EMF. Take note that the voltages that we are having here, this is the peak voltage and the peak current. So the peak voltage here is 283, and the peak current here is what? 5.66. But in the question, you'll be needing the vein RMS, that's the root mean square value of the voltages, not the peak voltages. You will not be using the peak voltages to solve the question. You need the vein RMS values. Okay. So now, with the frequency of the EMF, this is the EMF, the voltage. So how do you find the frequency? So realize that if you write a normal voltage source, you get V of M sine 2 pi ft plus our phase angle. So now the 2 pi ft is the same as our omega t. So from here, we can say 314 is equal to 2 pi ft. So t takes t away, so we get 314, which is equal to 2 pi f divided by 2 pi divided by 2 pi. So now you do this, you get a frequency of what? 50 Hz. When you solve this, you get a frequency of 50 Hz. Now the second question says that we should calculate for the R and the L. The R and the L simply means you should calculate for the reactance and you calculate for the inductance. Take note, the inductance is always measured in Henry. So you should calculate for the reactance. That is, in short, the resistive reactance. And you should calculate for what? The inductance. Okay. Now how do you go about calculating for the actance and the inductance? Now we have to convert the voltages into their respective VRMS. So now, from previous videos, we learned that VRMS, the VRMS voltage is equal to the peak voltage on root 2. And the IRMS voltage is equal to the peak current on root 2. Okay, so now to get the inductor R and to get the reactance R and the inductance, we need to find the impedance. And the impedance is simply equal to V on I, because from V is equal to IR, so V is equal to IZ. So with the resistance here is impedance in AC circuit. Okay. Now this V is VRMS, this R is RRMS. So therefore, this will give you 283 on root 2. Sorry, on root 2 divided by 5.66 divided by root 2. Okay, so when you do this, you are getting 50 ohms. When you calculate this, you are getting 50 ohms. Okay, so after this, you can also calculate for the phase angle. We need also the phase angle because within the current and the inductor, we need the phase angle. But take note that we said the inductor IL will always lead the current. So the inductor will always lead the current. So the inductor is having a phase angle pi on 6. The current is also having, the voltage was having this. So in the inductor, we said the voltage will lead the current. So sorry, the voltage is the one leading the current. So this is the voltage leading the current in an inductor. So the voltage will lead the current in an inductor. So you have to find the phase angle. To find the phase angle is simply the pi on 4 minus negative pi on 6. Because the value here, sorry, in the question here was negative. Sorry. So you can correct that, do solving. The value for the phase angle here was negative. Okay, so negative pi on 6. And that will give you, if you do this, you are getting 10 on 24 pi, which is equal to 75 degrees. So if you do this, you are getting 10 on 24 pi, which is equal to 75 degrees. Okay. So now since you have this, you can go ahead and look for our R and the L. That is our reactance and the inductance. So our R is simple Z cos theta. Z cos theta. So you can check on the value, the diagram, the previous lesson, and bring out this formula. But it's very simple to bring out this formula because you know that always our R, the resistive one, will be here. And this will be our Z. So to find the R, it's simple as the Z cos of the angle, which is here, the phi angle, which is the theta. So this is very simple for you to bring out. Okay. So now if you do this, our R simply becomes 50 cos the angle 75 degrees. And that will give you 12.941 ohms. That will give you 12.941 ohms. Now, how do you calculate for the inductance? Take note that we said the inductive reactance, which is XL, is always equal to the omega L. So the omega times the inductance. So therefore, from here we can say the L is equal to the XL divided by the omega. And now you calculate that. You know that the omega is always 2 pi F. But how do you find the XL? How do you find the XL? So now this is very simple. From the diagram I drew, this is the reactance, this is the inductive reactance, and this is our Z. So if you want to find this, it's simple the Z sine of the angle, the phase angle phi. You sine the phase angle phi. So if we do this, our XL simply becomes 50 sine 75, and that will give you 48.296 ohms. Okay, that's our inductive reactance. So from here, we can now find our inductance as L, which is equal to the inductive reactance as 48.296 ohms, all divided by 2 pi F. And the F is the frequency we found here, which is 50 Hz. So 2 pi F. And therefore, when you do this, we are getting 0.154 microfarad. 0.154 microfarad. Okay. Now let me clean here and do the last question. And the last question says we should find the power absorbed. So the C aspect of the question says you should find the power absorbed. And how do you calculate for the power absorbed? It is very simple. So the power absorbed now becomes the active power. The power absorbed is always the active power. So now, if you draw your diagram, here is the active power, just your reactive power, just your apparent power, which is IV. So the key here becomes the S, or what you are getting here, the value you are getting here, the S sine of the theta, and this one becomes the S cos of the theta. So to find the power absorbed, which is the active power, is simply S cos of the angle theta, or the phi. And the S is IV, so which is equal to IV cos what? Theta. Now we know our I. Our I is the RMS value over here. So the RMS value, which was 5.66 root of 2. So we get 5.66 divided by root of 2. Our voltage is also the main RMS value, which is multiplying 283 root of 2 times the cos of the angle theta, and the angle is what? 75. So if you do this, the power value you get is 207.256 watts. Take note, the power absorbed is always the true, the real, and the active power. And that one is measured in watts. The apparent power is measured in volt ampere, and the reactive power is measured in volt ampere reactive.